This is Chapter 4, Linear and Quadratic Functions, Section 4.3, Quadratic Functions and Their Properties. A quadratic function is a function of the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. Because, of course, if a is 0, we do not have the squared term. It's a first-degree function, not a quadratic. The domain of a quadratic function consists of what? Well, remember how we found the domain of a function. Start with all real numbers. Then if there is a variable in the denominator, there is not, so skip condition 2. Condition 3 said if there's a variable under a radical of even index, that condition does not apply, so it consists of all real numbers. And if you like, in interval notation, we can make a note negative infinity to positive infinity. So we know how to graph the square function, and we also learned how to transform it in section 3.5. So we're going to use these properties and some new terminology to explore quadratic functions. The graph of a quadratic function is called what? When you graph one of these, what do we call that graph? It's a parabola. If a, this a right here, if a is a positive number greater than 0, the graph of the quadratic opens which way? It opens up. That's one of these, the ones that opens up. And if a is negative, the graph opens down. So that's one of our square functions that has reflected over the x-axis. Remember, the negative outside the function made it flip. The lowest or highest point of a parabola is called the vertex. And the vertical line that passes through the vertex of the parabola, it's vertical and it goes through the vertex, is called the axis of symmetry. What that means is it cuts your parabola into two symmetrical pieces, perfectly symmetrical. You could fold it on that axis of symmetry and it would match up point to point. Okay, we're going to first talk about quadratics in what's called vertex form, and it's called this because when it is in this form, we know we can look right on here and tell that the vertex is the point HK. Now notice it's x minus h. So if that was x minus 2, what would h be? Well, it would be 2, right? If it was x plus 2, then in this form, that would be x minus negative 2, right? So we have to remember that. The equation for the axis of symmetry, it's a vertical line, right? So it's x equals, and it's x equals h. That it goes through the vertex, remember, so you've got this point is your vertex, and you've got a vertical line going through that vertex, so it must be x equals h. Again, if a is positive, this a, which is the exact same as this a, if that's positive, the parabola opens up, and if it's negative, the parabola opens down. Okay, we're going to look at two ways to graph parabolas, and the first one we're going to use is the transformation method. So here's how we will do that. We'll start with a function that's in this form and complete the square so that we put it into this form. We'll complete the square on x so it will look like this. Recall that when you complete the square, you take a trinomial and write it as a binomial squared. So you can see that's why that's completing the square is what we'll do. We have to, and then we will graph the function using the transformations that we see here, right? Outside the function, inside the function. This would be a compression, a vertical compression or stretch. Here's a horizontal shift. Here's a vertical shift. So we'll use all that to graph. Okay, so example 1, let's try this out. We are to use transformation, so we need to get it in that transformation form. So we'll complete the square on x. Now, when we completed the square before, we were working on two sides of the equal sign. Now we're not. This is in function notation, so we are not working on both sides. We're on the same side. So recall what I need to do is take this, the second degree and the first degree part of the trinomial. I'm going to add something to that so that this will factor to a binomial squared, but I've got this -1 here, right? That's not the right number. It won't factor to a binomial squared with the -1. So I'll move that over to the side. But if I'm going to add something here, and all of this still has to be equal to x squared plus 4x minus 1, then I'm going to have to subtract that same amount. So I could add 10, and as long as I subtract 10, then I haven't changed this at all. It's just not simplified. So I can't just add to this function, just randomly add a number. But I can add a number and subtract the same number. So let's see how that works. Recall what we add. It's 1/2 of b squared. That was the complete the square method. b is 4, half of 4 is 2, and 2 squared is 4. So if I add 4 to this, I have to subtract 4, because if I simplify this, it better get back to these three terms, and it does. So now, this part is a trinomial that when you factor it, you get a binomial squared. Remember, this is always my half of b. b is 4, half of b is 2, and then -5. So my vertex form now, I have it in vertex form, but this is also the form that gives me my transformations from the original squared parent function to now this transformed function. So what do we need to do? Let's make a note. For f of x equals x squared, the points we've been using were what? We used plug in -2 and get 4, plug in -1 and get 1, plug in 0 and get 0, plug in 1, get 1, and plug in 2 for x and get 4. Let's transform those to this function, the x plus 2 squared minus 5. All right, so what do we have to do? We do not have any flips. We do not have any compressions or stretches. We just have a horizontal shift which direction? Left 2 and down 5, right? So every x -2, every y -5. So for this point, -2 minus 2 is -4, -1 minus 2 is -3, 0 minus 2 is -2, 1 minus 2 is -1, and 2 minus 2 is 0. And now -5 for the y values. 4 minus 5 is -1. And 1 minus 5 would be what? -4. And 0 minus 5, -5. And 1 minus 5, -4. And 4 minus 5, -1. So now we're graphing our transformed quadratic. -4, -1, -3, -4, -2, -5, -1, -4, and 0, -1. So recall our original would have been at 0, 0. That point now is the point -2, 5. That's this point. Now that's the vertex, right? It was in the parent function, the vertex is 0, 0. In our transformed function, the vertex is -2, 5. So we didn't compress or stretch or flip, but we did shift it to the left 2 and down 5. Okay, in this next example, it says, identify the vertex and axis of symmetry without graphing. We're to locate the vertex and axis of symmetry. So the way we do that is we put it in vertex form by completing the square. So let's go over completing the square again. Now, recall to complete the square, we cannot do that unless x squared has a coefficient of 1. So I've got to factor out a -3. it'll be factor out negative 3 out of positive 6. I leave negative 2x. So I'm factoring it out of these two terms. I'll still have my plus 1. And then whatever I do here, I've got to undo there, right? All right, so I've got this plus blank. I'm trying to complete the square here. I'm supposed to add half of b squared. b is negative 2. Half of negative 2 is negative 1. Negative 1 squared is 1, right? Now, I've written that I've added 1, but have I actually just added 1? If I distribute and combine like terms, is that what I've done? No, because this negative 3 times that 1 is actually what I've added. I've added negative 3, so I've got to add positive 3, so that if I distribute this and combine like terms, I get back to this. Okay, so don't forget, here I didn't have anything but 1 in front, but now I have this negative 3. Okay, so this is f of x equals negative 3 x half of b, negative 1 squared plus 4. It asks me to locate the vertex. The vertex is the point hk. H is 1, k is 4. And the axis of symmetry is the vertical line x equals 1. X equals h.